you'll be always concerned by the processing of any signal. Okay, and even in other specialties, all the problems will be brought down to signals that you will have to study. That's why it's good to know, I think, and to understand all the process of processing signal, and especially the terminology or the technical words going with this field. Okay, so here for this first MCQ or MCQ number 3, you have the first question, which is just a matter of terminology here to know what's about. And they're asking you what is single valued function. It means just the definition of a single valued function. Does anyone know that, or may just guess, or at least choose one randomly, or proceed by elimination, as some people do, till you get to the right answer, of course. And here the meaning and the 4 definitions they give you are, the first one says single value for all instances of time. That means that it's kind of constant function. Okay, that means a single value, just one value. For all instances of time, that means that we have a constant function. That's the meaning of that. The second says unique value for every instant of time. Unique value here means that at every time, at every instant of time, we have just one value. Okay, but it's not the same as the coming one or the preceding one. The values are different. But for any instant of time, we have just one value for our signal. Okay, then we have a single pattern followed by after t intervals. Here they're talking about pattern, and we are not concerned about pattern. We're concerned about function. And here is also the last one, talks about different pattern of values is followed and so forth. Okay, the pattern means the tendency, globally how it works, how it moves, how it changes. That's what we call the pattern. And here, what do you think? Which one fits more the question they give you, the single valued function? Just give a guess, you don't have to be right for this question, since it's a new definition for you. Say something? Or I hope that all the people have the text. Don't you? Do all have this in front of you?
Yes, yes.
Yes, okay, so there is no problem with respect to the texts. So what I said, the first question, what do you say, A, B, C, or D? I can help you, You proceed by elimination. We just eliminate C and D. So we have just A and B. Which one choose? You just throw coin,
I
You
think
see
the
what you
upper.
get.
I think
You
the
think
upper
the upper one?
single value for all
Yes,
instances.
indeed. Yeah. This definition misleads you, Indeed, since they repeat the word single, so we tend to say that indeed the definition of a single valued function is A. But it's not A. Unfortunately, it's B. Why? Because for A, as I said, it's a single value. That means we have the same value for all time points. However, for the second, we have unique value for every instant of time. That means that for every t, we have a specific value. And they say unique value because, for example, if you take a function just like, let's say square root, okay? Square root of 4, that means that t is equal to 4. So what is the square root of 4?
2.
Or?
Um, It's true. There is no.
Or, I said or. Come on, boy, you know it.
-2?
Minus 2, of course it's minus 2. Minus 2 times minus 2 equals 4. Yes or no? So here it doesn't correspond as definition to unique value. It's not unique value. So for time t equals 4, we have two corresponding values. So it doesn't belong to this class of signals of unique value for every instant of time. So the single valued function are all the functions where for every instant of time, we have only one value of the function. Okay, just a definition. The second one is easier. How is time defined here? That's a general case, you know, or any function. Whether it's valued or complex. I mean, real or complex.
Time is relative.
Time is what?
Is relative. Einstein theory. Yeah, it's
We stick just to the definitions they give you. You know, you have A, B, C, and D. Okay, we're not dealing with Einstein here.
I would say it's real.
Yes, of course, it's real. Every time the time is real, you know. No matter, you know, how the function is. It's a real function or complex function, but we always work with T, and T is real. Okay?
Yes. Okay.
Anyway, okay. Number 3. Another definition.
So C.
You think that it's C.
Yes.
Here they're talking about discrete time signal.
Yes.
And it's derived, of course, from continuous time signal by
Sampling.
sampling. Indeed, the process of sampling is just taking a sample. A sample, what does that mean, a sample? Just taking part of something, okay? Very small part of something. How do we do that? Is that we take some points, equidistant points, of course, at the same distance to each other. And this process, that's what we call sampling. Addition, we know it, it's not. Addition, multiplying, it does have nothing to do with that. And addition, multiplication, of course, is not. So the only one remaining is sampling. Okay? And we'll be back in the future about this notion of sampling that we will develop. Okay? We'll extend and explain exactly the process of sampling and how we compute that and so forth. Okay? So that's good. And samplings, another just last word, is just we move from, for sampling, a continuous values of time, okay, in the beginning, in our continuous function. The time takes all the values. Also, it takes an infinity of values. And when we go to sampling, of course, time, we take only some values. Okay. Equidistant, of course, values, as we've said. Okay, number 4. Another definition, which is good to know, of course.
Yes.
False, sir.
Yes, boy, go ahead. The new one, yes. Okay, you say it, man. What do you say?
I say it's true.
You say the other guy who wanted to speak, I think. Who is he?
I choose the response B, false.
Can you tell me why it's false?
Because symmetric about horizontal axis.
The
That's it.
horizontal axis, yes. And here,
Vertical is
signals are symmetric. Yes, the vertical axis. Vertical axis. We call it even signals. Is that true or not?
not,
Even.
sir.
Even, let me tell you in French, even is pair.
Yes.
Okay? So, how are even functions? Are they symmetrical about the vertical axis or the horizontal axis?
It's
Vertical, sir.
What?
Vertical.
The vertical axis, of course. Okay? So here the answer, of course, is true. And we have all the times, we have x of t is equal to what?
X minus t.
X of minus t, yes. That's only for even signals or even functions. Okay, so remember this word of even, which corresponds to pair in French. Number 5.
Sir, can I
And
answer?
here you notice that it tells us that x of t is equal to minus x of minus t. So how is the signal called?
what signal?
What signal? They give you the definition. They say if x of t is equal to minus x minus t.
It's odd signal.
Yes, it's here,
signal.
it's an odd signal.
Yes.
Odd in French means impair. Right? And it's symmetrical about what?
The center.
About the origin or the center.
Yes.
Okay? So that's an odd signal. 2 words to know and remember all the time, even and odd. Okay, let's move to 6 now. And here we're dealing with complex valued functions. That means that x of t contains a g, okay? And from all the statements they give us, the 4 statements they give us, according to the question, there is only one which is valid. And for this, you can't take just a complex function. For example, x of t is equal to a plus gb, or x of t is equal to exponential of gt, and you do some calculations to check which one is true from all the definitions they give us here, or the equalities they give us. Mr. Aliwa, let me just remind you that we start at 8:30, not at 8:53, okay? So we are at 6, yes.
I don't understand the question.
You don't understand the question. Let's say here we have a function, a complex function, x of t, okay? When we say complex, that means containing a g.
Okay.
All right. And they say which one of all the equalities they give you here, the 4 ones, which one is valid? Normally, only one is valid. All the rest, is to be rejected. But which one is valid for complex functions? Because we talk about conjugate here, okay? So when we talk about conjugate, that means that we have a complex function.
The A.
The A.
Yes. Conjugate before X conjugate T.
Yes. What do you get?
I choose A.
What's A? Which function did you take to check that? Did you take any function?
Any function, yes.
Yeah, which one did you take? Just as an example, We just made x of t is equal, as I've said, to a plus gt, for example. Is a complex function. Or
Yes.
we also can take x of t is equal to exponential of gt. Okay? So you have just to look for x of minus t, then look for the conjugate of x. And see for the first case here whether they're equal or not. And you do the same for the rest of the equations.
It's B.
So-called-
B. I think.
What? It's B.
Yes.
I don't know. Your classmate said that it's A. Mr. Eub, let me just tell you the same thing, as I said to your classmate. We start at 8:30, not 8:55. Okay? Especially there's no transportation problem. So which one is it? A or B? Since we have two answers.
Yeah, I'll go for B.
You go for B.
Yeah.
You must be convinced, Okay, let's assume that x of t, our complex function, is given by exponential of gt, okay? So what is x of minus t? What is it?
It's a minus, it's exponential minus GT.
Okay, that's exponential of minus gt. And what's the conjugate of x of t?
It is X negative T. That's it.
We're talking about exponential, the function exponential. I said x of t is equal to exponential of gt. So what's the conjugate of x? The conjugate, what do we do?
Is it exponential minus gt?
Yes, of course. We just reverse, the imaginary part. So it's exponential of minus gt. And what did we say about x of minus t?
So it's the first answer that's right.
So indeed, the first answer is right. Yes, for all complex functions. The second one, it can't be true because we have said that x of t is equal to exponential of gt, and x of minus t is equal to exponential of minus gt. So they can't be equal. And the third one, what do we have? Minus x of t, which is minus exponential of gt, and x of minus t, which is exponential of minus gt. So they're not equal. Here we're inversing the time, and here we are inversing the amplitude. And so is the last one also is not true. So the right answer here is A. Okay? Let's move to 7. Please, you pay attention to this kind of questions, to negative questions. And here they talk about non-periodic signal. So which one among all these definitions corresponds to a non-periodic signal? You all know the definition of periodic signal. Okay, it repeats itself, every period. Which one is that? Though the definitions are very clear.
I would say C.
You would say C.
Yes.
Okay, is there any other idea? Any other opinion? Don't forget, we are looking for non-periodic signal. So can you tell us, Miss, why is it C?
We have the same x t plus grand T.
We have the same. So if we have the same, what does that mean?
Sir, I said that because I think that the definition here is not applicated for periodic signal. We all know that the definition of periodic signal is supposed to be xt equals to xt plus big T.
X, not X, X.
Yes.
Yes, indeed, but let's see. How about the first definition? The equation x of t is equal to x of t plus t is satisfied for all values of t. Is it periodic or not? Is this function periodic or not?
I think we have a constant value for T.
Yes, a constant, but you can take any constant. That's what they mean here. Okay. So is it periodic or not?
No.
Why?
Because we just have one value for big T.
Yes, I know. That's let me give, for example, an example. I'll give you a function x of t, and I ask you to draw for me the periodic function x of t plus t with t is equal to 2. Can you draw it? Can you draw it or not?
Yes?
Yes, of course. Another guy of your class, I will ask him the same question, but putting t is equal to 5. Can he draw this signal or not?
Yes.
Yes, of course. So both signals are correct and both signals are periodic signals. The exception is that the value of t differs from one to another. But both of them, they got a periodic signal. That's the meaning of satisfied for all values of t, whatever t is, real, of course. The thing now, we have x of t is equal to x t plus t is satisfied only one value of t. Is it periodic or not? Only one value. That means that here I give to all of you only one value, the same value to all of you, and ask you to draw the signal. So is it periodic or not?
If xt is periodic, it's going to be periodic too for each value of t, for every single value of t.
What? With respect to this one, to b. What do you say? Is this signal periodic or not? Okay, we give one value to t. We give it t, the value of 10. So we have x of t is equal to x of t plus t.
Yes?
What does that mean? Is it periodic or not? So signal repeats itself in order to say that it's periodic. And he insists it repeats itself for specific period t. That means, of course, that the signal is periodic. But at the opposite, for c, what do they say? X of t is equal to x of t plus t for no values of t. No values, even 0. That means that in this case, we always have x of t is equal to x of t, since t is equal to 0, or no value, doesn't exist at all. So here x of t is just equal to itself. So we cannot say that it's periodic, it's non-periodic. And the last one also, of course, is periodic, because we have a value for t. Even though it's only odd values or even values, we don't care. The most important is to have a value for t, and we do have it here. So again, this signal is periodic. So the only one which corresponds to the question here is indeed, as the lady said, is C. Okay? How about 8 now? Now we are dealing with, or will be dealing with, discrete signals. Since we're talking about x of n, not x of t.
It's A.
It's
A.
A. Can you read it, please?
Omega equals 2 times pi over n.
Over n, yes, indeed. It's omega is equal to 2 times pi. I think the British, they say p. Americans, they say pi. Over n. What is n? And here, of course, we're talking about periodic signal. Okay? Since you have omega.
Yes.
Which equal normally to 2 pi f, the frequency, or over t, which is the period.
Yes.
In the continuous case. In the discontinuous case, of course, we use n. And in this case, n corresponds to what? Mr. Sadah, let me tell you that we start at 8:30, guy. Okay, boy? How do we choose n? N N is we have continuous signal, and we sample this signal we have set. N corresponds exactly to the number of points we have within one period of time. Okay?
Okay.
That's the N. Since in the continuous case, N corresponds to T, the period. Since it's discontinuous, so we take the number of points we have just within one period. Okay, so omega always equal 2 pi over N. Okay, we go on. Please, if you have any question, don't hesitate to interrupt me. Nine, here we come to a new definition. And here they're talking about noise. And noise, you know, you'll find it everywhere almost. Because whatever device you use, there are always some perturbations due, of course, to the outer noise and the outer electromagnetic waves and so forth, and sounds, etc. So noise will always exist in any chain that you're dealing with. So how noise is classified or characterized?
It's random signal.
Why is it a random signal?
Because it's random.
What's the meaning of random in this case?
Random means there is no pattern.
There is no pattern. No, it does have a pattern, you know. But the problem here is that we cannot find any mathematical equation describing this pattern. Okay? For A, they say discrete signal, or the signals are discrete or continuous, so it's not the answer. B, it's deterministic signal. What does that mean, deterministic signal? That means that the signal has a corresponding mathematical equation, cosine, sine, trigonometrical equation, or exponential, or whatever it is. Okay? But it's described by an equation. So we can work on it by using, of course, the different transformations that we know, Laplace, Fourier, or whatever. But a random signal is a signal which does not have, as I've said, any description, mathematical description. So how do we describe it, this signal, since we don't have any equation on hand? How do you describe this signal? Random signals?
Cannot be determinated.
Yes, if you want to process this signal, and you will have to process random signals, you know, in your studies. How do you do? What are the tools that you will use?
Apply a filter. Use a filter.
Filter?
Yeah.
No, I'm not talking about eliminating. Not eliminating. How would you describe? How do you characterize this random signal? We just do it, you know, by their statistical characteristics, which are, for example, the mean, the variance, and maybe correlation factor, and energy or power, and so forth. That's how we characterize these signals, random signals. Okay? Since they don't have any equation. So we use just statistical parameters to describe them. Okay. Number 10. Very small calculation here. No, not yet. We don't have any calculation. True or false? And tell me why.
I think it's false because
You think it's false?
yes,
Okay, you keep speaking. Tell me why.
because if I remember, the equation of energies and power are defined by a surface, and there is no surface on this figure.
There is no surface. No, boy, let me just tell you. That is figure A. Figure A goes with question 11. Okay?
Oh.
Not 10.
Oh, okay.
You need a cup of coffee, you know. Okay, and strong coffee, Arabica. Yes. 10. They just give you a definition, and they ask you true or false.
Power signal has infinite energy, so it's false.
So it's false. What did you say? Why? Say it again.
Power signal has infinite
Energy signal. Power signal has what?
infinite.
Infinite energy. Why?
That's what we studied.
That's what you studied. Okay. So, in the beginning, they say that energy signal has zero average power. Why? You know that the energy and power are connected by what? Are connected by time.
Yes.
Since we know that the energy is a product of the power with time.
Yes.
Yes or no?
Yes.
So if we have an energy signal that has zero, it's an energy signal, since we know the energy. And they say that has zero average power. So the power is given by the energy over time, the time tending to infinity. Okay? So the power will be indeed equal to zero. That's what we call an energy signal. On the other side, when we have power signal, in order to get the energy, what do? We multiply this power by time, with time tending to infinity. So we get an infinite energy signal, and not zero energy. Okay? Do you understand why? And just by the way, miss, please, don't try to remember things that you have learned and say because that's what they told us. Try always to connect things and to understand the physical process happening, you know, in all these points that we are covering, and even for you, so you can rediscover this every time and not just to learn by heart. And maybe, you know, your mind will be once in a while, it might be defection, you know, in your mind, and you will be misled. So the relationship between energy and time is energy and power is time, and you just manipulate this equation in any way you want. So indeed, it's false because here it's infinite energy. Okay. Okay. Now let's come now to our famous figure A. And as you see, it's periodic signal. And they ask you what is the fundamental frequency of discrete time wave shown in figure A. Which one is it?
Excuse me, sir, can you please repeat how you justified the 10th one?
The 10th.
Yes.
Oh, the 10th. Yes. Okay. That's you who told me, I think, that that's the way you learned it. Okay? Yes. I said that energy and power
Are
are
connected.
related, are connected, yes, related to each other by time.
Yes.
Yes or no? The energy is given by the product of power with time. Okay, that's why we calculate the power is given by kilowatt or watt, and the energy is given by the kilowatt hour, for example. So here, the first definition, this energy signal has zero average. What does that mean? That means the energy signal, that means that we have a value for the energy, for example, 10. In order to get the power, what do? We divide the energy by time, knowing that time t tends to infinity. That's the limit always. So when we tend t to infinity, of course, the power becomes zero. Okay, though the signal had a specific energy. This is true for the first half of the sentence. But the second half says that power signal. That means that we have a value for power. And to get the energy, we have to multiply this power by t, with t tending to infinity. It's always a limit. So the energy will become infinite energy and not zero. Okay?
Okay, thank you.
Okay, never mind. Tell me just the next one. 11. Just give us the fundamental frequency here.
What is the period?
What is?
The period of
The period.
signal, yes.
That's what you're asking your boy. You have everything. You have beautiful figure and nice expressions, mathematical expressions. And you have seen before, if you remember, that the fundamental frequency of periodic signal was given by 2 pi over n. I think that's you who said that. And I gave more details about this expression of, in general, 2 pi over n. So here in this specific case, what's the fundamental frequency? It's very important. They call it fundamental frequency. Why? Because if you remember, when you've studied the Fourier series, okay, for periodic signals, and you present the signal in the frequency space, okay, what do we get? We get at the origin, of course, the constant value, which was the mean. Then we get the different harmonics. And the first harmonic corresponds to omega 0, the second one to 2 omega 0, the third one to 3 omega 0s, and so forth. And the first one, omega 0, that's what we call the fundamental frequency, because it corresponds to the frequency of the initial signal we're studying, periodic signal. So here, how do we define this fundamental frequency? Knowing that this fundamental frequency is given by 2 pi over n. And what have I said before? I told you the meaning of n. What was n?
Number of impulse?
Number of
Impulse.
not impulse. I said
Sir,
before that.
for this one, I choose C.
You think it's C. But first of all, would you answer my question? I said, what's the meaning of n?
Is the number we took.
The expression we have seen before, I don't remember exactly well. Yes, question 8. Okay, we've seen fundamental frequency n is given by.
Yes, we chosen
We said
A.
pi over n. What?
We chosen A in the task
Yes,
8.
me too, yes. Yes, okay, yes, you have chosen E or A, yes. So, here, which one is that?
C.
You say C, why? How did you get that? First of all, answer my question before that. N, the capital N in question 8. What does that represent? Though I explained it.
Is that the number of sample?
Number of samples, yes. For which
The N.
time? Yes, for which time? Oh, these people's coming in and out. Oh. Period of time. Which samples do you take? I said that we take the number of samples which corresponds to one period of time. Since it corresponds to the t in the continuous case. Okay? So here in our case, specific case here, figure A, how many points do we have for one period of time?
3.
What?
No.
One period of time, I said. You look at your signal here.
4.
6,
Figure A.
6, sir.
What?
6.
Say it louder. I can't hear you, miss.
6. I said 6.
6. Oh, okay. Get just the microphone close to your mouth. Yes. Yes, indeed, it's 6. As you see, it starts from 0, for example. And where do we get back? Or again, this value? So as you see, we have 3 ones, followed by 3 minus ones. Then we get back to our initial signal at 6. So indeed, the number of points representing one period of time of our signal is 6. So what's the answer for 11?
B.
It's B.
It's B, of course, it's pi over 3. Okay, is it a little bit more clear now? Okay, so give me that one. 12. Rapidly, please, because we are a little bit behind of time. Very small calculation. And you are dealing here with continuous signal. Very easy one.
What is the
Don't forget,
value?
we are dealing with figure A. Don't forget, it's still figure A, the previous figure, okay, that we had before. Okay, so what's the average power?
0, I think.
The average power is 0, you think. Why is 0?
Because it's discrete.
How do you compute your power? Your average power.
It's the surface of.
It's not, boy. We are not dealing with surface. I said figure A. It's the
Yes.
previous figure. Okay. Well, still above, you know. That's a discontinuous signal that we have in figure A. And we're still talking about the signal. They say calculate the average power of the discrete time wave shown in figure A. So what is it? The power. How do you compute the power? And they're talking about the average power.
So we were able to use a relation about limits, something like that.
Yes, of course. That's what we use. In the continuous case, it's 1 over t, the integration of x squares of t dt.
Yes.
That's what we use in the continuous case. But here we are with discontinuous case. So what is it?
It's still a limit of one.
Limit of what?
The power of a discrete time signal.
Yes. So what is it?
It's 1 over 2 times. It's a limit of n goes to
N.
infinity.
N. Limit of.
Yes, n when it goes to infinite of 1 over 2
Not, but
times.
not the limit of n. The limit of 1 over n. Yes or no? In the continuous time, it's the limit of 1 over t for the power. And here, what do we have? How many samples do we have in one period of time in t?
6. We have
So we have 6, of course.
Yes. Each
So what is it?
example gives us 1 watt.
1?
Watt.
1? Yes, power, yes,
B,
watts.
B.
Yes, of course, it's 1. It's a. Which answer is that?
It's B, no?
B6. How did you get 6?
Because we have 6 samples.
Yes, 6 samples, but over n. It's power, not energy.
Yes, then it's 1. It's A.
So it's A, indeed.
Yes.
That's 1 over n, which is 1 over 6. For one period of time, we have 6 points.
Yes.
And the summation of the x squares for this period of time, of course. And since we have only once, whether 1 or minus 1, it's a square. So it's 1 plus 1 plus 1, 6 times over 6. So we get 1.
Yes.
Okay, guys? Okay, let's go now to continuous signals. I think that you feel more at ease, with continuous signals. Which are very easy to process. What is total energy? Rapidly. 13. The energy now we're talking.
It's 4A.
Wrong.
Wait. Not 4A. 2A.
Not wrong.
Oh.
You know at the exam, since it's going to be an MCQ also, For any wrong question, you have minus something, okay? So pay attention to the wrong answers. The energy. How do you compute the energy of this signal?
The energy. I thought it was the power.
You don't have to think, you have just to read. And they say total energy.
Sir, we use integration.
Yes?
We use
Of
integration.
course, it's continuous case, yes. Since it's continuous.
It's for a power 2.
Shame on you, boy.
Yeah.
You got 3 wrong answers.
أنا الأولى سيبه.
And consecutive wrong answers. How come it's very easy calculation to do here? The energy, what's the energy? Is the integration of x squared dt. So what does that mean? That means we integrate x is 2a. That means 2a squared from -1 to 1.
Yes.
So what do we get? 2a squared gives us 4a squared. We get out of the integration. And
It's
we have
a
dt,
squared.
integration of dt, which gives t from -1 to 1. That gives 2.
Yes.
So it's 2 times 4a squared.
It's 8a squared.
Thank you very much. Very good. Yes, of course. That's the only answer left, you know, due to your friend, of course. Okay? So indeed, it's 8a squared. Just 2 expressions, you know, that you all know, and we try to apply here. Now, we have found the energy. Now we go back to our power. Okay? How do you compute the power?
It's still an integration. The period is 1,
It's
right?
not periodic signal, boy. It's not periodic signal here.
The T is equal to 1, right? From minus
Yes,
T to
t takes values from -1 to 1.
Yes.
It doesn't take just one value.
So the integrate goes from -1 to 1. That's what I'm trying to say.
Yes, of course, from -1 to 1. But how do we find the power? The
Sir,
power is a limit of something. We have said that something before, if you remember. In an upper question, I don't remember which one. They gave you just definition, the relationship between power and energy. Yes, miss?
It's connected.
the signal have finite energy, so he must have 0 power.
Yes, indeed, 0 power. But tell me why? I
Because he
explained
has
that to you before twice.
Because he has finite energy.
No. In this case, no, it's not infinite. Here, it's energy.
Finite.
We have the energy.
Finite.
Ah, finite. Okay.
Finite.
Okay, when you have finite energy, what happens to the power?
Zero.
We have said 0. Why? Because we have said that the power is given by the energy over time, the limit of t, when t tends to infinity. So, of course, it's 0. Okay? That's the same relationship, you know, between energy and power. And here we come back to question 15, another discrete signal, and they ask you to give the total energy rapidly, just in 1 second, normally. Because the energy is always easier to compute than the power. It's because you don't have any division to perform.
It's 6.
It's
6. I go for A, I'm not sure.
or A.
Yes.
What all the rest of the class think? The energy is given by here, since it's a discrete signal, where it's given by summation of the x squares, okay? And all the x's are equal to 1 or minus 1. So the summation of all these points will give us, of course, 1 plus 1 plus 1 plus 1 gives 6. So the right answer indeed is A. Okay? Is there any question? Okay, so without interruption, we go rapidly to the second MCQ. Okay? And we have to do it a little bit faster, than usual. And this one will cover also very, very interesting points that we use when we process any signal. That are the average values and, of course, the RMS value, which is the root mean square, or the effective value. That's what we call in French la valeur efficace. Okay? And the average value is what we call also in French la moyenne. Okay? And there's a big difference between these two parameters. And they are very characteristics of every signal. Okay? First of all, they ask you to find the average value rapidly of 3 values. They give you here 4, 5, 6. What's the average?
It's 5.
It's 5. Of course, it's 5. Okay? Number 2. That's what I call just warming question, just to warm up. Number 2.
So the average current, no?
Let's just look at the definition. Found by finding the current in equidistant region, and here that means that they're taking a discrete signal, okay, of current. So they take a region, they take the number of currents they have in the region, and they divide by n. N is the number of currents they took. So what's that?
The average current.
That's the average. That's exactly what we did in the first question.
Yes.
Okay? Just the difference is that in the first one, they were very precise values. And here they're talking in general. So if you take any interval of time, you take as many numbers, as many values of you want, okay? And you divide by the number of values that you have, and this corresponds automatically to the average current. 3, definition.
It's A.
I said that before, okay? So indeed, it's the root mean square. Why? Because in the definition of the RMS, we have a root to perform, we have a mean to perform, and we have a square. Okay? The definition for the RMS value of any signal is given by the square root of 1 over t, okay, or 1 over n, the summation of all the x squares. So we have a root, we have a mean, and we have a sum. That's the definition of the RMS. 4. Another rating. What is it for?
It's this RMS current.
It's RMS, and that's it, you know.
Just that's it.
Okay, indeed, that's the definition of the RMS. This is obtained by finding the square of the currents first, and then finding their average. Okay, we sum up all these squares, we find the average, then we find the square root. So this is the RMS. Okay?
Okay.
Number 5. Another definition. What is that? It's continuous case here. Since they're talking about the area. So it's continuous function. What is it?
I think it's the average current.
Yes, of course, it's again the average current.
Yes.
How do we compute the average current? It's 1 over t integration from minus t over 2 to plus t over 2 of x of t dt. When we have, for example, an even function, okay, even, symmetrical,
It's, 2 over t from 0 to t.
from 0 it's 2, okay?
Yes.
So what do? We take half of the area and we take half of the period. Since 2 over t means 1 over t over 2, okay? And it's nothing but the definition of the average current,
Yes.
okay? Number 6. Get very easy one. The other way now. Get them incrusted in your mind, you know, these definitions of average and RMS.
RMS current. Yes.
What is the effective value of current?
It's the RMS.
It's the RMS. I said that in the very beginning. We may call it the root mean squared, the RMS current, or the effective.
Valeur efficace. Yeah.
Yes, that's what I've said also in the beginning. Yes. Okay, guys? Okay. Now, we go to applications. Okay, we stop with definitions. We know everything. We take specific case of sinusoidal wave. What do you think? And we want to compare the average current with the RMS value. Are they equal? Which one is bigger, or no relationship? You know that. And we're talking about sinusoidal wave. Okay, don't worry, just speak. You don't have to manage your voice. Oh, it's not a theater here.
Sir, since the RMS value is the square root of the average value, so I think the average value is greater.
Pay attention, miss. The RMS has never been the square root of the average value. For the average, we compute the integration of x. For the RMS, we compute the integration of x squared.
Yes.
So there's no relationship between the two.
Okay.
The RMS is superior, greater than the average.
The RMS
So
is yes.
the average is always less than the RMS.
Just an example. That's why they give you here. They say in a sinusoidal wave. What's the average for sinusoidal wave?
It's the middle. No,
Wow.
not sure.
With no offset, of course. There's no offset here.
No, I'm sure.
The average. And you know that the average is the integration of the function. And the integration, you have seen that before, corresponds to an area. What's the area of sinusoidal wave within one period of time? You always have half of the area is positive, it's over the t-axis, and the other half is below the t-axis, is negative.
Yes.
So what's the average?
Zero?
Of course it's zero. Wow, you say it in such a way, you know, as if you haven't seen that, never, you know, or heard that before.
Yeah, if
Of
if you do the sum,
What?
you get zero.
Yes, you do the sum, of course.
Yeah.
That's the summation of both surfaces, of both areas.
Yes.
One is positive,
Yeah.
the other negative. And as is the case for all any alternating signal. It's not only for sinusoidal waves. Rectangular waves, triangular waves, as far as they are, of course, alternating signal, which means that we have the same area over the t-axis as the one below the t-axis. The average is always equal to zero. And there's no offset, there's no shift, okay, of the curve to the up or to down. Okay, and how about now the RMS? The RMS is never zero. For sinusoidal wave, what is the value of the RMS? We have done that. What's its value?
It's 0.7 of the
Wow. 0.7.
yes,
How
of
is it
the peak.
It's the peak. Yes.
It's
What do you say? Say it clearly. It's the peak.
peak of the sinusoidal
Yes.
wave.
It's the maximum value. Yes, that's the peak.
Multiplied by 0.7. You get the
Multiplied by 0.7.
yes, you get the RMS. I'm not sure.
How did you get 0.7? How did you get 0.7? I don't know. But usually it's given, you know, another way. We know that the RMS for sinusoidal signal is given by the maximum value, that's what we call the peak,
Yeah.
over the square root of the
2.
2. Yes. Okay? So since the RMS always depends on the maximum value, or the peak, or the crest, that means it's never equal to zero.
Yes.
Cannot have a curve whose maximum is equal to 0. It's not a curve. So that's why we always have the average current is always less than, smaller than the RMS. Okay?
It's lesser.
Let's move on. 8. Here they give you very concrete examples.
It's same. The
What do you mean?
average is 0
The average
current.
for a rectangular wave, boy. We are not talking about sinusoidal wave. It's a rectangular wave. There is no negative part here.
Okay.
It's not an alternating signal here. It might be a periodic signal, but not an alternating signal. So what can we say? You can just take a very small example, you know. Of a rectangular function, periodic rectangular function, whose period is t, for example.
Yes.
You compute the average and you compute the RMS. Very rapidly, since it's constant value here, you don't have to integrate anything. So what do we get? Hey guys, it seems to me that I'm in front of just two people, you know. A gentleman and a nice lady. Where's the rest of the class? What is it here? For 8?
It's equal to
Oh,
RMS.
I forgot to go to the chat. Even for the chat, you know, there's nothing, you know. No people, no one is chatting. Yes, okay? Who's talking? Mr. Jalil, Fodil, yes.
Yes. What is
Yes, what can you say?
what is the equation of the average current in a rectangular?
Hey, come on, boy, what the expression? The expression is the same, boy, for every signal. It's 1 over the period, integration from 0 to the period of x of t dt. That's the average. So what is it here? The average and the RMS value. Okay, the average is given by the I said 1 over t, which is okay the width of the rectangular function, 1 over t.
The period. Yes.
Yes, you say period or whatever you say, you know.
The t.
Let's assume that we have only, yes, it's what?
T. The t is the period.
Yes, the t if you want is a period, yes. So it's integration of a from 0 to t. You get the a outside. So it's integration of 0 to t dt. So it's t that you cancel with the other t, with the 1 over t in the beginning.
Yes.
So we
it's
get
A.
a. Yes. How about the RMS now? It's the same thing. It's the square root of 1 over t, integration from 0 to t of x squared dt. What is x squared? Is a squared. You get
1 minute.
integration.
I lost it in RMS. Didn't follow. Yeah, we said
At
it's
least- at least-
the average.
No, at least you are with me, you know. Okay.
The RMS.
Yes,
the
I said
RMS.
the RMS is the square root of 1 over t,
Yes.
okay, of times the integration from 0 to t of x squared of t dt.
Okay.
X squared is a square,
Okay.
but you get out of the integration. So integration from 0 to t of dt, which gives t, that you cancel with the other t, and the square root of a squared is equal to a.
Okay. Yes.
Are you okay? Are you with me?
Yes. Yes. So it's equal. The average.
It's
and,
equal, exactly.
the
That's the exception. In all the cases, we always have the average is smaller than the RMS, except for a rectangular wave,
Okay.
where they are equal.
Okay. Okay.
Okay, folks?
Okay.
Let's go on rapidly, please. What do we have?
2 more questions.
Peak value now.
Peak value divided by the RMS value gives us.
Gives us what? The peak value is the maximum value
Yes.
of a function. So if we divide this peak value by the RMS, what do we get? Maybe something new for you. But how do we call it?
The crest factor.
It's the crest factor or the peak factor also.
Okay.
Okay, it's the same thing. Peak or crest factor.
Okay.
How
In
about the
the-
last question, Ken?
Okay.
Small
Calculate
calculation.
the crest factor if the peak value of current is it's 5. 5 ampere.
Hmm?
Oh, it has no unit. Right.
Boy,
Has no
it's volt
unit.
over volt, boy.
So it's no unit. Amp.
Of course, it doesn't have any unit, boy.
Yes, it's 5 then.
It's the peak value divided by the RMS. Both of
Yes,
them
five.
are in terms of volts.
Yes.
So there's no unit. So it's
5.
I. There's no I.
5. Say A.
Ah, 5. Ah, okay,
Yes,
it's
A,
A.
A.
Yes, of
Answer
course,
A.
it's A. How about sinusoidal form? What is the peak factor for sinusoidal wave? You have seen that before. I told that before.
The peak.
The peak factor, I said.
Oh, I think it's 0.7, if I'm not mistaken.
0.7. How do you get 0.7? You're 0.7.
Oh, no, it's square root of 2.
Square root of 2, of course. That's
Yes.
what you've said before. We've said that the RMS is given by the peak value over square root of 2. So the
Yeah.
peak factor is equal to the peak over the RMS. That means square root of 2.
Okay. Yes.
Okay, guys. I'm a little bit disappointed, to be honest, because I feel just like very few people are with me, though all the rest are present, I know, I think. But I would like you to participate more, to say anything, what you have in your mind, even though it's wrong. We are here to correct this and to explain things. But I need more contribution on your part. Okay? It seems to me that I'm doing the lesson, instead of you today. I hope it will be better the next time, because this notion of RMS is very important, And you will have to, and you will meet this notion, you know, everywhere you go. Why? Because when you take a current, okay, sinusoidal form, for example, if you, at home, you take a multimeter, or what we call a matrix, okay?
Okay.
And you want to check the value of the voltage that you have at home.
Yes.
So you go to any outlet, une prise,
Ouais.
the outlet, you take the voltage. What do you read? Which value do you get?
Efficace. C'est RMS.
What?
RMS. Yes.
Value, the value, give me the value, the number.
217 or 220.
Yes, it's not constant. Yes, here you're very right. You know, sometimes you have to 20 to 30 to 40. It depends. Okay,
Yes, yes.
on the on the mud of sonel gas or the mood of sonel gas. Okay, so here the value that we get at the outlet level is indeed corresponds to the RMS. Though the signal that we're taking is sinusoidal wave. But sinusoidal wave, what does that mean? That means that it varies all the way, all the time, goes up and down. We know its peak, okay? And the matrix that you have, the multimeter that you have, takes, of course, the shape of this wave, sinusoidal wave. It does, there is a processor inside it, does all the calculation, which is square root of 1 over t integration of x squared of t dt. Then it gives you this value of RMS. And in another way, physically speaking, what's the meaning of RMS? The effective value. What's the meaning of that? It means exactly the following. If you take a resistance, you connect it to an alternating signal, okay? So you will get certain power dissipated through this resistance, okay? And we have used alternating signal current. And the RMS means what is the value of the continuous now, not alternating, of the continuous current that you must use, or voltage, that you must use to get exactly the same power dissipated through this resistance. Okay? So that means if we take two resistances, that we connect the first one to the alternating signal, the 220 volts, we have a power dissipated, you get some heat, and in parallel, you connect the same resistance to a battery, okay? Direct current, continuous current, which gives 220 volts. You must get exactly the same power dissipated through both resistances. Okay, that's the meaning of the RMS. Because of course, we can't work with alternating signal. It's always varying, its value. So we need something constant. That's why we use the RMS, or the effective current, all the time. Just before I finish, let me tell you something, or remind you something, you know. In the very beginning, we have talked about this famous report that you must send me. And normally it must be sent by the end of next week, okay? But still, unfortunately, for your specific section, I haven't received any report. It's not late, since you still have till the end of next week. However, let me just remind you 3 points. The first point, as I said, the report must be between 4 and 5 pages. Secondly, the report must be written in the form of the IEEE standard. You must respect the standard that we have studied in the first class. Okay? And also, annually, it must be submitted, as I said, by the end of next week. Okay? Such that I'll be able to program any people who want to do the short presentation, you know, even through what we are doing online. They can do it. Okay, guys?
Presentation online, sir.
We don't have any choice, boy, unfortunately.
Yes,
Okay.
we want it that possible online.
You You know, I don't have the choice. You're talking about the presentations.
Yes.
Yes, we do them online. Is there any other way? There's no other way. We don't have any place at the university, you know. Because for us, we keep studying online, even the last 3 weeks. Okay? We don't have presential for us. Because it's not fundamental course. Between quotes. Okay?
Okay, sir.
That's why we
Thank you, sir.
to do it online. I don't mind. Okay? Never mind, boy. Any question?
What is this report all about? We choose a subject.
On which planet were you, boy? During the first and second class.
I have it. I have the format of the.
Yes, but I spoke about that. You know, I told you to take the project that you have done in L3 for your master's degree.
Okay.
Yes, you take this report, but you know very well in French, just to make summary, you know, of 4 or 5 pages. That's it in English, and to write it, you know, by using the IEEE format and send it to me. That's it.
Okay.
Okay? Never mind. Any other question? Okay, so see you next week, inshallah.
Inshallah.
Bye.
Salam.